Converting between logarithmic and exponential equations. First thing you want to do is remember that the logarithmic equation or the logarithmic function is actually the inverse of an exponential equation or an exponential function. So why don't we write that relationship? Base b raised to the y power is equal to x if and only if a y is equal to what? Log base b of x, where b cannot be 1 and b has to be greater than 0. The other thing you got to remember is the domain of the logarithmic function. That is, x has to be greater than 0. We're ready to convert. So if you're given an exponential equation, as in part A, our goal is to write it into a logarithmic equation. So here it's given in an exponential equation, and then we just got to write that the exponent is going to be a log base b of an argument called x. So our base is 6, so our exponent, I should start with the exponent. The exponent is -2. -2 is equal to log base b, which is 6, and then the argument is 1 over 36. If it helps, you could put the parenthesis here around the x, and that certainly makes it look more like a function. I'll give you an idea here, like f of x is equal to log base b of what? Of x. You can see that the input is actually x, just like function notation. Let's go to the next problem. The next problem actually is an equation, and it says to convert this equation into a exponential equation. So here you have a log equation, and now we're going to go to the exponential equation. Oh, by the way, if and only if is what we call in mathematics a biconditional. It's basically a two-way street. So I'm going to put a double-sided arrow here. So if you start on the right side, you can go to the left side. If you start on the left side, you can go to the right side. So that's what an if and only if symbol looks like in mathematics. It's actually a double-sided arrow. So if we're given a log equation, we're going to go to an exponential equation. So log base 8 of the argument 1 is equal to 0. So we're going to start with the base. The base is 8. And we want to know, our exponent is 0, and that is equal to 1. And of course, from your mathematical knowledge, you know that is true. That is a true equation. Next one, you're given a logarithmic equation, and you want to get this into an exponential equation. This time we'll start with the base. The base is 8 again. And raised to the -2 power, or the opposite of 2. And that's got to equal what? 1 over 64. Part D says you have a log equation, and now you want to change it to a exponential equation. Start with the base. So our base is 4, raised to the exponent of 3, and that's got to get you 64. The next one, we start with an exponential equation, and you want to write the log equation. So the exponent, 4, is equal to log base 3 of the argument, which is 81, or our input value of 81. One last one here. We have an exponential equation, and we want to write it into a log equation. Our exponent is 0, so we're going to start with 0 is equal to log base 3, and our argument has to be 1. And there we go. We've written an equivalent equation given a certain type of equation. And the reason we could do that is because exponential equations and logarithmic equations are related. The exponential function often has an inverse that is a logarithmic function. So that's why we keep going back and forth, back and forth, back and forth. Rewrite each equation as requested. So here's a logarithmic equation, and we're going to try to write it into an equivalent exponential equation. First thing we want to do is write the definition of a logarithm. It's related to an exponential equation. It is actually base to the exponent is equal to x. If and only if the exponent y is equal to log base b of the argument x. And of course, we need b to not be 1, and we need b to be greater than 0. Now let's write the definition in a special case where the base is actually e. So let's write e to the y is equal to x if and only if y is equal to the natural log of x. Now remember, if and only if is a two-way street. So if you start with the left, we can go to the right. If you start with the right, we can go to the left. It's what we call in mathematics a biconditional. Let's start with part A. The ln of x is equal to 9. Let's write its equivalent exponential equation. This has to be e to the 9 is equal to x. Let me try to make this a little bit easier for you guys to read. Let me write this in a different color. Y is equal to the natural log of x. So the parentheses there indicates the function notation. You could say f of x is equal to the natural log of x. And now it sort of matches the function notation. The function here is called the natural log. So that's why we could put the parentheses around the x. You typically don't see it in books. They expect you to read it as invisible parentheses, which I think is sort of brutal. There's enough invisible symbols in mathematics. Rewrite as an exponential equation. ln of x equals 3. We want to rewrite this as an exponential equation. Well, it's just like part A. So e to the third power is equal to x. How about we go the other way? What if you're given an exponential equation, e to the x is equal to 8? How do we write that? By definition, we need to write x is equal to the natural log of 8. The exponent is first. Rewrite as the logarithmic equation for part D. So the thing I remember is if you want to switch to logarithmic equations, you actually start with the exponent. So 2 is equal to what? The natural log of y. It's the only thing left. If you knew that, I wanted to ask you this question. What is e raised to the natural log of y? Try to figure that out. What is this equal to? Going to part E here, we want to rewrite this as a logarithmic function. So if it's a logarithmic function, we start with the exponent, which is y, is equal to the natural log of 8. This time we have a log function. In part F, we have a log function, a natural log. We have a log equation. We have a natural log equation, and we want to switch this to an exponential equation. So we're going to start with base e. E raised to the exponent is equal to the argument, which is 5 in our case. Let's circle our final answers. Let's evaluate each of these expressions. So we just want to change the way this looks. Let's see what these look under different properties of logarithms. I am going to do this in a simpler method, and that simpler method is using formulas. Log base 5, I'm sorry, not log base 5. Why don't we generalize this to log base b? So what is log base b of 1? We already know that's 0. We already know that log base b of 1 is 0. What is log base b of b? Log base b of b is equal to 1. And then what is log base b raised to the b to the p power? Well, that's just p. So knowing those three properties and a review of what does it mean to have a opposite exponent, remember what it means to have an opposite exponent means take the reciprocal of a and then raise it to the n power. Or some of you might remember it as a to the opposite of n is 1 over a to the n. In either case, you're really just reciprocating. All right, why don't we change the way these expressions look? To save room, I am going to work across. I usually do not, but let's write that as 5 to the negative 2, and that is equal to negative 2. So we changed the first expression to look like this new expression called negative 2. Oop, I'm writing too much for this one. We know log base 7 of 7 is equal to 1. That's 0. And this is log base 2 to the second power. It's really this one right here is equal to 2. Let's circle our final answers. And there are other ways to do this, but since we are starting with expressions, the only thing we're writing here are expressions. One expression is leading to another expression, is leading to another expression, leading to another expression. There's no equations involved here, so be careful with what you're reading. You're just writing expressions. The equal symbol means to have the same value. The equal symbol here means to have the same value, but there are no equations involved in this problem because we are manipulating expressions, or we're simplifying expressions. Let's graph some logarithmic functions. And remember that you want to use your own graph paper. You definitely want to label everything. You got to label the domain and the vertical asymptote when we talk about logarithmic functions. Why don't we spot the domain of g of x right now? Remember that you could only take the logarithm of a positive input. So the input has to be positive here. So we have to say x is greater than 0. Well, that implies that the domain of g must be what? 0 to infinity, because it does ask for interval notation. Now, we need some ordered pairs. Actually, hang on. Because we got the domain, x is greater than 0, we also have the vertical asymptote. The vertical asymptote actually is the vertical line x equals 0. So we got the vertical asymptote. We're going to need that. Now we're ready to find some inputs and outputs. So here's x, and then our output is g of x. Let's say, well, we should definitely look at 1. Actually, I do want to get close to that vertical asymptote. Why don't we try 1/4? If we try 1/4, we get positive 1, right? So if you look at g of 1/4 is equal to the opposite of log base 4 of 1/4. But that's just the opposite of log base 4 of 4 to the negative 1, which is the opposite of negative 1, which is 1. Of course. What else could we pick? Well, we certainly could pick x to be 1. And the opposite of log base 4 of 1 is 0. The opposite of 0 is still 0. And why don't we pick x to be 4? If x is 4, we get the opposite of 1. We're ready to graph this. You can also use translations or transformations as well. But when in doubt, pick some convenient ordered pairs, label your vertical asymptote, which is x equals 0. There it is. X equals 0 is our vertical asymptote. 1/4, we need 1. So let's say this is 1 and this is 1. At 1/4, we need to plot up 1. So right about here. 1, 0 is plotted as well. And then 4, negative 1. 2, 3, 4. Let's say that's 4. Let's extend this out. That's 4. We need a negative 1. So 4, negative 1 is right here. We have a vertical asymptote. So draw your function. Make sure you draw it in a way where it passes the vertical line test. And so this logarithmic function is actually decreasing from left to right. And it has a vertical asymptote at x equals 0. Make sure you circle your final graph with all its labels. It did ask for the domain. You should always label the vertical asymptote. And then label your ordered pairs. So circle all your labels and circle your graph. Basically include all the details. Let's not call the second function g. Why don't we change that letter? Why don't we change this to... what letter do you think? What letter comes after g? Why don't we change it to h? Why don't we say this is h of x? Hello, h of x. All right. Once again, we need the domain of h of x. We can only take positive inputs. So the first thing you want to notice is take x minus 2 and make it positive. So that implies that x has to be greater than 2, which implies that the domain of h is in fact 2 to where? To infinity. That also implies something else. That implies we also have a vertical asymptote. And it is what? It is x equals 2. That's going to come in handy. Let's get some ordered pairs. Get some convenient ordered pairs here. The input is x. The output is h of x. Let's pick x to be 3. If x is 3, we're in good shape. Because that's just negative 3. The output would be negative 3. What else could we pick? Why don't we pick x to be 6? If x is 6, we get 1 minus 3, which is negative 2. And I'm going to say that's enough. With the vertical asymptote and with 2 ordered pairs, you could sketch this graph. Let's draw some axes. 1, 2, 3, 4, 5, 6. 1, 2, 3. So this is -3. This is +6. I need to plot some ordered pairs, but let's first graph the vertical asymptote. That's going to be very, very handy. That's really key. Let's graph the vertical asymptote, which is x equals 2. And let's plot these ordered pairs. 3, -3 is down here in the 4th quadrant, and 6, -2 is in the 4th quadrant. And I believe that's enough to figure out what this logarithmic graph is going to do. It's going to do something like this. It's actually increasing from left to right. It's growing very, very slowly. Well, actually, it grows very quickly at first, and then after x equals 3, it starts to grow slowly. Let's circle our final graph with our labels, vertical asymptote. Make sure you put arrows at the end of your graph so it matches your domain and range. Oh, it did ask for the domain and range. Let's go back and find the range for both these functions. Not a problem. If you need to find a range, turn your head 90 degrees to your left, and then you try to read from bottom to top. So notice the range of g, if you're reading from bottom to top, is simply -infinity to infinity. The same for the function of h. The range of h is equal to -infinity to infinity. And what do I mean by turning your head sideways is you should be able to see your infinity symbol down here because you're reading from bottom to top. And it does go where? It does go to infinity slowly, but it does go to infinity. So that's why the range is read along the y-axis. And remember, the domain is all your possible inputs, which is from left to right. Now let's circle an additional final answer. And we've answered all the questions. As usual, graph on your own paper. Graph and label everything. Label your ordered pairs. Label your vertical asymptotes. Let's find the domain of these functions. Both of them are logarithmic. So you just got to remember, you can only take the log of input values that are positive. So the first thing we're going to do for part A is make sure x squared minus 9 is positive. Now, this should remind you of polynomials. You have a polynomial that can factor to x plus 3 times x minus 3, and we want that to be greater than 0. We're going to take those zeros of those polynomials and put them on a number line. And we want to see if we could test the x values in between them, and we're going to test the inequality. Let's call this inequality here double star. We're going to go ahead and test that inequality. Just make sure you indicate what your test values are. So let's test x equals -100, x equals 0 in the middle, and then x equals 100 here. And remember, you're testing the double star inequality. If you test x to be -100, you have a negative times a negative, which is positive. So that is going to be true. And we want the true regions, so that's true. If you test x equals 0 in here, 3 times a -3 is a -9 greater than 0. Well, that's false. We don't want that. So all those values in between represents a false situation, and we don't want false. We do not want the false region. One more test, x equals 100 in this double star inequality. A positive times a positive is still positive, so that's going to be true. Awesome. And now we could shade from left to right what your true regions are, and don't shade the false region, and then we keep shading here. So from the very, very far left, we started with -infinity, and then we end up shading the concept, or shading to the concept of positive infinity. So let's write our final answer in interval notation. What is the domain of f? The domain of f is negative infinity up to negative 3, union negative 3 to infinity. Let's find a domain for g of x. Remember that we could only take the natural log of positive inputs. So we need 9 over x minus 6 to be greater than 0. There are no zeros to this rational function. So what we do need to worry about is this situation here, the vertical asymptote. We know that the domain of this rational function, 9 over x minus 6, x can't be 6. So we just got to test the region around 6. The two regions around 6, I should say. So put 6 on the number line. And then we got to test the x values. Let's call this inequality triple star. Once again, just indicate what you tested. Test x equals 0. Over here, test x equals 1 billion. This side's going to get you false. I don't want this side. Notice 9 over negative 6 is not positive. That is going to be false. That's a false inequality. How about 1 billion? Oh, that one's going to be true. We got a positive number over a positive number. Is it still positive? Yes, it is still positive. So we have a true region here. We can't shade 6 because we don't want to divide by 0. So shading from left to right, we have parentheses, and then we shade all the way to the concept of infinity, and we put parentheses on that as well. So the domain of G is equal to 6 going to infinity. And we have that. We have that. What do you need for work? Lots of stuff here. Everything here. Make sure you're able to show all this. Show your work. What's over here? Same over here. You need to show your test values. You got to make sure you show or indicate what your test values are, and you're testing some kind of inequality. Expanding a logarithmic expression. Use the properties of logarithms to expand this. The log of the argument x to the 4th over z. So it really looks something like that. There's the argument. There's your input. It's actually x to the 4th over z. Now, what are some of our log properties? Some of our log properties say to do this. Log of m over n is actually equal log of m minus log of n. So we're going to go ahead and do that. Let's do part A. Let's manipulate the expression in part A. Remember, if they don't indicate a base, it's really base 10. Now we do have another log property, and that is log of x to the power is equal to the power times log of x. So we're going to do a 4 here. We're going to put that 4 as a coefficient of log of x minus log of z, and this is as expanded as we can get it to be. So let's circle that. How about part B? What do we do with part B? Well, there's another log property. Let's say it's log of r times s. That is going to equal to the log of r plus the log of s. So how can we rewrite the expression log of y times x to the 6? I'm going to rewrite that as log of y plus log of the argument x, log of the argument x to the 6. And we have log of y plus, we're going to take that 6, make it into a coefficient, and this is expanded as much as we can do, or much as it can be. Let's circle that. Let's write the expression as a single logarithm. So we're going to change the way this expression looks. We're going to manipulate it, keep changing it, keep changing it, keep changing it. And we're going to use order of operations for part A here because there's a parentheses. Let's change this expression to look like a different expression. We're going to do order of operations first. So in the parentheses, we're going to raise that 4 to become an exponent on the x. And now we are going to condense some of these things. We still have parentheses, so we're going to do parentheses again. This is going to be log of what? Base m w over x to the 4th. All right. Now we're ready to do a little bit more. Log base m z to the 3rd power plus log base m w over x to the 4th raised to the 2nd power. And we're getting warm. We have one more thing. We got to get this into a single logarithm. So log base m, and we're going to multiply now. Z to the 3rd power w squared over x to the 8th power. And we're done. Written that first logarithm into a single logarithm. So we're just manipulating expressions here. We're just changing the way the expressions look. How about the second one? This one here is equal to, first thing you want to do is take all those coefficients and make them into exponents. And we're going to read this from left to right. Order of operations says we break ties by performing from left to right. So the first thing we're going to do is log base 5 of x to the 1/2 power times w to the 4th. Times w raised to the 4th minus log base 5 of y. One more property here. Log of the square root of x times w to the 4th over y. And we have a base 5 here. If you want to, you might want to put parentheses here so you can see the input. We've written that expression into a single logarithm. Why do we want to write multiple logarithms into a single logarithm? It really helps with solving log equations later on. So that is really why we're actually condensing like terms involving logarithms. Let's try part C. Once again, we want to take that coefficient and make it into an exponent on the argument. The argument here is actually x minus 7 minus log base m of x plus 7 and then raise it to the 7th power. Now we have common logs because they have common bases. And now we're going to use one more log property to get this into a single logarithm. Log base m, and then we have a bracket here, x minus 7 raised to the 2nd power over x plus 7 raised to the 7th power, and we're done. Looking back at things here, I do want to state certain conditions. Here x can't be 0 for sure. But we already knew that. Even up here, we knew that w is greater than 0, x is greater than 0, and z is greater than 0. Notice here y can't be 0, but we knew that already. Y was greater than 0, w is greater than 0, and x was greater than 0. And over here, x cannot be what? X cannot be negative 7. And this, we sort of knew that as well. We needed that x minus 7 is greater than 0, and x plus 7 is greater than 0. What does that really mean? X is greater than 0 and, x is greater than 7 and x is greater than negative 7. So that means it really implies that x has to be greater than 7 for part C. And so we know that x cannot equal 7 already. It says use the change of base formula to compute this logarithm. And there's a second logarithm as well. Why don't we label this as two separate problems? Let's say this is problem A and this is problem B. And we got to know what the change of base formula says. It says take log base A of B. And we could rewrite this as what? We could rewrite this as a division of two other logarithms, and you get to choose the base you want. So typically we could say log base k of b over log base k of a. There's a lot of restrictions, of course. A can't be 1, and a is greater than 0. K can't be 1, and k is greater than 0. Because you get to choose any base, I highly recommend that you choose base E. It's a little bit more natural, and for those of you taking calculus, you would definitely want to know the natural logarithm anyway, and the graph of it and the domain of it. So it makes sense to try using base E for your change of base. Let's do the first problem. Log base 1/6 of 1/8. Let's change this to a computation for natural logs. So let's change this to the natural log of 1/8 over the natural log of 1/6. And I'm sure you could put that into your calculator and find out what that is. Keep in mind, this is a negative number divided by a negative number, so we should get a positive number. In fact, you should get this, 1.160558, and it keeps going forever. It says round to the nearest thousandths, so we need the 10,000ths position, which is this 5 here. 5 or more tells us to round up, so we are going to round up to 1.161. And we could circle this as our final expression. Notice there are no equations involved in these two problems. We're just changing expressions. We're just manipulating the expression and changing the way it looks. Let's look at the expression log base 7 of 1/6. Once again, I am going to use the change of base to be base E. Log base 7 of 1/6 is now going to equal the natural log of 1/6, which is a negative number, divided by the natural log of 7, which is a positive number. So we should be expecting a negative number here. You might be wondering, how do I know the numerator is negative? That is because when you are graphing functions, you're doing them by hand. And every time you graph a function by hand, you have a chance of memorizing them. And then, of course, memorizing them to truly understand the mathematics behind it. So there is the natural log function called ln of x. And what is this? Well, that is the x-intercept. So that's 1, 0. And then do we have a vertical asymptote? Of course we do. The vertical asymptote is x equals 0. So how do I know the natural log of 1/6 is negative? Because the graph says so. Look at 1/6. If this is 1, x unit of 1, 1/6 is over here, and the y value is negative. Anyways, the number you should get should be negative a decimal 92078. 8, and that's enough. It does keep going forever. I need to look at the 10,000ths place. In this case, it's a 7, and so we are going to round this up. We are going to round this up to negative 92, well, the magnitude. We're going to round the magnitude up to decimal 921. We'll circle that as our final answer.